How is the audio now? I'll use my radio voice. How is the audio online? I can't hear you, but I know we have folks monitoring that, so I will get the we'll make any changes as needed. Let me unshare and reshare. This is where I do my geothermal stand-up bit while the slides are transitioning. So I think we should be good on the slides, and we'll go ahead and get going. Bring up the chat for questions. So thank you very much for having me. I'm really excited to talk about geothermal systems today, and I'll do that in a way that approaches it from the petroleum system perspective. So it's of course, petroleum systems are something I came from as well. So we'll talk about what is geothermal. It sounds like an adjective in search of a noun. So we'll talk about what that means generally. As I mentioned, we'll talk about petroleum systems vis-a-vis geothermal systems. And talking about geothermal is also not done without the context of the technology used for geothermal, whether that's power generation or direct use. So we'll get into that a bit as well. So this won't just be subsurface geoscience. I know there are some engineers who have slipped in here, so most of them wearing sport coats. So we'll be able to talk engineering as well as geoscience here. I'll talk real slow. So what geothermal is, kind of the vision of the pot of gold for geothermal, is that it's mining heat out of the subsurface. It's not mining water or other fluids. It's simply using those fluids as a carrier at the highest level. Water is really just the pass-through mechanism.
Share a different screen. Let's see.
Technical difficulties. So when I was in Iceland last year for a geothermal conference, there were a bunch of folks walking around with hot and steamy t-shirts. So I've been trying, some of you have heard my hot and steamy jokes before, or the jokes about exploration in geothermal is really all about what's hot and what's not, and figuring out the difference. So those, we could keep going with that, but we'll get down to the science. So for the online crowd, you missed the title slide. As well as my geothermal talk summary, which we have there. So again, we're mining heat out of the subsurface, and there are a variety of ways that we can mine heat rather than using the water. The fact that we don't use the water is very important when it comes to water law and water rights, because there's no beneficial use of water here unless you're using it as part of the direct use. That takes out a whole legal and regulatory frame that would otherwise potentially be quite a headache. So with petroleum systems versus geothermal systems, we've got our the ones we know and love in the petroleum side. We've got source, we've got maturation and migration, we've got reservoir, and we've got trap and seal. And of course, we can throw preservation in there as well. When it comes to geothermal systems, they're pretty similarly related. We've got the thermal source. We've got the quality of that thermal source. We've got migration of heat, and we've got the reservoir that the heat is contained in. Again, usually contained as in water or in fluids in general. So we'll get right to the source. And a lot of geothermal talks leave out discussion of the source. And this is where I can bring in a little bit of astronomy to this talk. So we are there on the third planet from the sun. And the fact that we're on a planet is rather important when it comes to sources. Our planet sits in the habitable zone. So we're in that Goldilocks zone where things are just right. We're not too hot and we're not too cold. As all the planets formed, they formed from accreting masses that spun with gravity and formed into a sphere. And that heat of accretion is about half of the heat remaining deep inside the planet. The other half of that heat comes from radioactive decay of uranium, thorium, and potassium elements. So there is a sustained source of heat, but also that heat flux of from the beginning of the solar system is important as well. So it's interesting to note that period of accretion called the late heavy bombardment, which was not the time we would want it to be here on Earth. That's when the last of the secreting heat was coming in. And so it's literally the impact, the frictional impact from all sorts of things coming in that provided that heat. And then once the gravitational mass of the planet became such that the Earth started spinning, that's when you started getting fractionation of various elements, denser towards the core and lighter as you go outwards. And so once that happened, it became an irreversible process. That's also what began and kickstarted the convective mechanisms deep inside the Earth that circulate that heat from deep in the core outwards, and becomes important when it comes to how heat still circulates to surface today. But that drives an interesting thought, which is that the core of the Earth is actually younger than the Earth itself, because it took that period of time of fractionation by density for the core to actually become the core rather than undifferentiated group of elements. So I'd mentioned radioactive decay earlier as part of the source. 2011 study that was published in Nature mentions that 54% of the heat flux to surface is radioactive decay. And that amounts to 44 terawatts in total, going from Earth's interior into space. And so it allows us to easily fall prey to the same thing the solar industry falls prey to, which is if we can just get a little bit, just a small sliver of those terawatts, that could power humanity. And humanity is getting there, but it's a very small sliver, certainly from both the solar perspective and the geothermal perspective. But it goes to show how much energy is in the subsurface that is there to get. So we have decay chains for those of you who wanted equations. I didn't bring in equations, but uranium and thorium and potassium, of course, are the key elements here. Then we can step more towards the surface, and this won't be a geology 101 lesson, but the tectonic processes near surface in a relative sense are what drives heat flux to surface. It's the asthenosphere and the mantle convection. So it becomes the ring of fire. The ring of fire becomes the most obvious place to look for geothermal, and that's of course where geothermal got its start historically in 1904 in Italy, in Iceland as direct use not too long after that, and really any volcanic area. But it's these same processes that give the West Coast its seismicity, that give the world its seismicity in the ring of fire, is what drives geothermal process. So when it comes to how we diffuse heat into fluids, we can bring up a more geothermal specific diagram here. And what we have here is kind of the key between interactions of the mantle and crust is hot fluids that get near enough to mantle processes, magma processes. So it really drives conduction in dry systems and convection in fracture and permeable systems through fluids. And when I say fluids, what I'm really meaning is water most of the time, but we can work with any fluid. The specific heat capacity of water is really good. It's 4.4 kilojoules per gram per degree centigrade. It's an awkward set of units, but 4.4 is the number to remember. Pure crude oil, WTI crude oil, has about 2.9, and gas is less than 1. So when it comes to any subsurface fluid, that can work for geothermal. It's just that particular fluid, depending on what it is, that can drive heat flux. So when we've talked about source, and we can move into talking about reservoir, and this is where the similarities with oil and gas become very strong. Reservoir focuses on flowability of the resource in sedimentary systems, just like in oil and gas. There are other subsets of geothermal outside of sedimentary systems, or that can involve sedimentary as well. One of them is enhanced or engineered geothermal systems, and that's where you're finding heat wherever you find it, and then you use a frac to unlock that heat. Sound familiar? Yes. It is that straightforward and that highly analogous. There's also hot, dry rock. And by hot, we could mean 500-600 degrees Fahrenheit or even more. So the deeper you go, the hotter things get. Those tend to need a frac as well, but because they are dry, as the name suggests, you hope that the system you find doesn't drink the fluid that you put down. So losing oil-based mud into a wellbore is your problems in considering hot, dry rock systems where it could drink everything you put down there, and then therefore circulating fluids or circulating closed loop fluids kind of becomes your only option down there. So some of the key reservoir qualities that we look for in geothermal are the storage, aka the porosity, and the flowability, which in some sense is a measure of the permeability, and that can be permeability from macro faults. It can be from larger natural fracture systems. And that's where seismic imaging can come in this world as well. Sometimes you can image, of course, macro faults. A lot of times you can sort of vaguely image areas with diffuse or profuse natural fracturing, but not always. So just as with oil and gas, there's always the uncertainty, particularly in the reservoir system, of how much storage do we have there and how much flowability are we going to get. And before we go too much further, something we can talk about is flow units and conversions in general. So if you talk to a European manufacturer of geothermal equipment, you'll get all your specifications quoted in liters per second. And they might be familiar with gallons per minute, but they won't know barrels per day. So being proficient trilingually, so to speak, in barrels per day, gallons per minute, and liters per second. I have a handy reference chart here. Feel free to screenshot. So US geothermal is a bit fluent in liters per second than others because most of the equipment does come from Europe and Asia in places where liters per second are important. But it's, again, with a bridge from oil and gas or between oil and gas and geothermal, it's important to be proficient in those. And if you Google barrels per day to liters per second or something, Google will give you a 31 or 32 gallon barrel. So you will be off if you do that. So make sure to develop your own spreadsheet and stick to it. So when it comes to prospecting for geothermal, I know we have some seismic folks in the room. So we have some size as well. Again, we need both heat and flow above at least the limits, the minimum limits of current technology. So if we think about a volcano, just your average cylinder or cone-shaped volcano, you've obviously got the heat here, not a problem. But you don't have the flow generally because you don't have too much of a fluid system, unless you happen to have something like the Rainier Beer reservoir, where it's a really good reservoir and it flows quite a bit through naturally fractured basalt. When we look to a sedimentary basin, like something over in Nevada, shown on the right, you can have the flow, particularly where the headwaters, the flow are up in the higher parts there, and the lower areas are the reservoir, but maybe not the heat. So again, it's all about finding both. And a nice thing about sedimentary systems is that we have a lot of data. The traditional geothermal industry works in fractured igneous terrains or areas they hope are fractured igneous terrains without a lot of data, very few or no well bores. And there has to be a lot of exploration. The average time frame to bring a traditional geothermal project online, according to the EIA, is approximately 7 years. From initial funding, exploration wells, going through another funding round, drilling of development wells, et cetera. But with sedimentary systems, we have thousands to tens of thousands to sometimes hundreds of thousands of oil and gas wells that all have bottom hole logs or bottom hole temperatures, as well as estimates of porosity, and in some cases, core data with permeability. So I've mentioned we have high flow rates, but of course, we can have high flow rates. But the oil and gas industry is focused on maximizing the value of hydrocarbons produced. And that doesn't always mean, and quite often doesn't always mean, maximizing the flow, particularly where variable 2 or 3 phase permeability comes in, where if you maximize the flow, you might actually shut off your flow of oil. So Oil and gas production data is very handy for oil and gas or for geothermal exploration in sedimentary systems, but it tends to be somewhat of a minimum in terms of what the reservoir can do. UIC permits, injection permits are very handy because those quite often do have maximum injection tests. And so you have a sense, what pressure do you need to inject what at what rate? You tend to have a lot of surface infrastructure. Again, it may be focused on oil and gas, sized oil and gas specifically. An example of that is a project that Transitional Energy is working in Nevada, is sized to flow 6,000 barrels a day. The DOE grant will help us bring that up to 60,000 barrels a day. So we're going to take it to flow an order of magnitude more fluid. And the porosity and permeability there is so high that one, we can do that, but it'll be interesting to see how the petroleum system responds as well. Whether the oil cut out there, which is currently 0.7%, will go up, will go down, but in a 25 to 30% porosity system with almost Darcy perm, there's not too many little nooks and crannies that oil can get hung up in. So part of getting to sedimentary reservoirs isn't just the which I refer to as the yay hot water phase. And I think a lot of LinkedIn is still on the yay hot water phase. Like, I'm a geoscientist, I can find fluids. I found hot water, yay. There's so much more to making geothermal happen. And part of that is the engineering around drilling the well or repurposing the well if you're using an existing well, logging it, and then completing the well. And sometimes your wells need fracs, they need acid cleanouts. They might need or have open hole completions. They might use or need to use slotted liners instead of plug and perf to get that 60,000 barrels out of, or 15,000, let's say, out of one well. A lot of oil and gas wells are 4.5 inch outer inner diameter casings. Those can work, but 5.5 is better, 7 is better still. And pretty much no one in oil and gas uses 9 5/8. But if you somehow had a 9 5/8 well, then you could really go to town with that. So there's a lot of overlap between all the flavors of engineering and geothermal as well. So I mentioned bottom hole temperatures earlier, and I think there was an asterisk next to that. And so anyone who's ever tried to use uncorrected bottom holes to make a map in a basin that is near maximum burial knows how much fun / frustrating / completely unusable bottom hole temperature can be unless it is carefully corrected. So you can have digital logs with that data, which are great. You can have any variety of nasty rasters to digitize. And so doing that at scale is always good fun. But here we have one with 220 in the middle, 243 degrees Fahrenheit, 294 on the left. So those all sound great, especially when you're using technology that only needs a minimum of 150 Fahrenheit to actually start making power. But obviously, the more the merrier with technology or with this technology. So the higher you can get to a reasonable number and then preserve that to surface, the more you have a sense of what the resource is you're using, you're starting with rather. So bottom hole temperature is the log header that records the maximum temp. I think everyone here probably knows that. But does that represent true reservoir temperature? And the answer would be no, except when it's maybe. But you can, if you have to have an answer for a cocktail party quiz, the answer would generally be no. So we have to correct that up to get a true estimate of reservoir temperature, because mud cools the system based on circulation rate, based on the mud weight, and based on the drilling rate. And so you can look, particularly in basins where you have many decades of drilling, if you histogram out uncorrected temperatures, you'll actually see histograms by age. By the 1950s, have a certain set with its own mode, the 70s, the 90s, and then newer horizontal wells. So if a well took a month and a half to drill in the 1950s, but going to the same zone takes 3 days now, that will be, that's an impact on the reservoir. There's much less of an impact now. So you generally see newer wells tend to show higher temperatures. And then, so that as a result, the concept of warm back is poorly understood. As the reservoir warms back to whatever the quote true measure is. So please never ever, I don't know when who would do this, Please never ever make a map with uncurved bottom holes, whether you're looking at oil and gas source rock maturity or whether you're trying to do geothermal. So there's a number of papers out there, as well as a website that allows you to do some initial corrections. And those corrections might be known as time since circulation is probably one of the better ones. There's Horner plots. There's other names of geoscientists who've reached immortality by having an equation with their name on it. But that's all datamed on hours. And because it's all based on Gulf of Mexico data, where you've got Darcy perm and you've got really good porosity. But if you're working in the DJ, particularly in a tighter zone or even in the Lion sandstone, let's say, the tighter things get, then the slower that warm back is and the less the Gulf of Mexico data, just like Archie corrections, the less that matters now. So transitional, we've had a guy working on some examples, and this is an example here on the left. This is the number of Colorado wells where we stripped out of the 59,000 or 61,000 digital logs that the state maintains. We pulled out the bottom hole temperatures and then pulled out time since circulation and came up with this plot. So up here, we're at 15, 20, 25 to 40 hours at max. We have very few wells where time since circulation is much more than 40 hours. And you've got a whole lot of wells where time since circulation is 10 hours or less. So that stands in contrast with this example here, also from the DJ Basin, where the x-axis starts around the 1st of March and goes to the middle of May. And we warm up from 150 to 240, so a 90-degree Fahrenheit warm up over about a month and a half, 2 months. If you ran your time since circulation numbers, you'd get maybe a 30-degree warm up. So you'd still get an upward push in what your true reservoir temperature might be, but it's not going to be 90 Fahrenheit. And now you could ask the question, well, could you ever see that on surface? Does that even matter if what's coming out of the wellbore is what it is? And of course, what comes out of the wellbore is basic. And so I'll talk a little bit more about some technologies out there that can preserve temperature to surface. And sometimes just more flow does that better. It lowers that delta between the reservoir temperature and the temperature on surface. So that if you take one thing away from this talk, it's that warm back can be over weeks and months and not hours when it comes to coming up with what true reservoir temperature is. So now we pivot a little bit into talking about the technology of how geothermal works. We've talked about the source and we've talked a little bit about reservoir. So geothermal started as steam and just steam coming out of the ground naturally in seeps was where geothermal first started. So when you, on the left-hand side here, this is a DOE example of dry steam comes up the left-hand side pipe. It goes as steam into a turbine where the smaller the pipe, the higher the pressure. It drives that turbine, which turns a generator and makes power, and then the water goes back in an injection well back into the subsurface so that there's a mass balance of the fluids longer term there. You can have a twist on that, or you can have flash steam. So you can bring the water up very hot, 300, 400, 500 degrees Fahrenheit, but bring it up as water and have the steam go into a flash tank where it only becomes steam at surface. And you go from 9 or 12 bar to 1 or 2 bar. And then that steam, after it's expanded in volume quite a bit, drives the turbine, makes power, and goes down the injection well. So that's been traditional geothermal, if you will, up to 10 to 15 years ago. And so the history of this technology is that the first geothermal power generation occurred in Larderello, Italy in 1904. There was an Italian prince, Prince Piero Giorno Conti. I'm not going to say the town he was from, but he thought we can probably harness this. We can take the work that 19th century academics did around how to take thermal energy and make mechanical work happen out of it. And we can at least power some light bulbs. He ended up powering initially some light bulbs and then the nearby section of the Italian railway. So I did get to work trains into this eventually. Nowadays, there's 800 megawatts of capacity at the same site. And there's, you can see the cooling towers for Larderello over here on the right-hand side. This is dry steam, so it comes out of the ground as steam, turns the turbine, very simple technology at its core. So when you step away from steam, you get into what's called the Rankine cycle, or the organic Rankine cycle. And so there's William J.M. Rankine. He was a 19th century scientist in Scotland. And based on the length of his beard, which I understand correlates directly to the influence that a male scientist could have at the time, it's a middle-length beard. We're not talking John Wesley Powell length here, but it's there at least. But he had developed, along with some French academics like Carnot, had done the math to figure out the idealized thermodynamic cycle, where mechanical work mechanical work happens as a result of extracting heat from a fluid as that heat goes from source to sink. So it wasn't until really the 1960s, actually the late 1950s, the two Israeli folks came up with a way to make developing country power grids more resilient. And that's the company that now is Ormat Technologies. They started and developed that world, first in turbines and then becoming a kind of a one of the only vertically integrated geothermal companies. But you've heard ORC, you've heard people say binary cycle power plant. They're the same thing. By binary cycle means you work with two fluids. And ORC is, and the organic side of ORC just means there's a working fluid that tends to be organic. It's something with a lower vapor point than water. So it's an isopentane. It's something in the 5 to 8 hydrocarbon realm. So in talking about working fluids, that gets us into modern refrigerants. So as water was the first geothermal working fluid, folks realized, wait a sec, we could make this work at temperatures lower than 212 at sea level or lower than 195 here in the mountains if we use different fluids that volatilize at 190, 180, 150, et cetera. So in the early 20th century, the air conditioning industry was just getting going, but they had a terrible problem. Air conditioning units kept catching on fire because the refrigerants were all highly volatile, highly flammable organic compounds. And so in the late 20s, 3 researchers came up with chlorofluorocarbons as a way to solve the problem of flammable AC systems. So as we know, one generation solves one problem. That became a problem with ozone holes in the 1970s and 80s. So one generation's solution is another generation's problem. So nowadays, those refrigerants have moved from being CFCs to being hydrofluorocarbons, which have an order of magnitude less global warming potential. Now to hydrofluoroolefins, which have the same global warming potential as CO2. So essentially you're down to a GWP number of 1, starting at like 12,000 where CFCs were. So modern refrigerants today, which are usually non-toxic, if anything, their only MSDS item is as an asphyxiant. So there's not too much hazardous with these things. This is a list of some common refrigerants. There won't be a quiz later, but we can point out everything has an R number, I've learned. So you've heard of R134A, which is what's in most automobiles right now. That's tetrafluoroethane. The geothermal industry here in the States and Europe for a while was using R245FA. Anyone who took organic chemistry can have fun with that compound. Here's the global warming potential. So the good old R12 and R22 from back in the day was again 10,900. Now we're at 1,000. And a lot of Europe is moving to R1233ZD, as they call it. So that's a global warming potential of 1. And it has essentially the same properties. So this is modern refrigerants working for you. And then air is R729. So you can say, well, next time you have an HVAC technician at your house, you can say, well, we've got a lot of R729 here. We're worried that it's offsetting the R134A in the system. And see if you get a blank look from them or not. It's like someone saying, well, we've done the gas analysis and it's 79% nitrogen. Congratulations, you've discovered air. So geothermal technology wouldn't be geothermal technology without heat exchangers. And sometimes you need heat exchangers. In organic system, in binary cycle systems, you do need heat exchangers because you've got to get that heat into the closed loop refrigerant inside the box. With a steam or dry steam application, you tend to not need this because either the steam is directly spinning the turbine or it's going through a flash cycle. There are two different kinds of heat exchangers. There's this one, which is a plate and frame, which sounds like, it is what it sounds like and what it looks like. The number of plates can vary depending on how much surface area you need to heat exchange with. And then the gaskets between the plates will vary based on your fluid type. So if you're heat exchanger with all oil, you use different gaskets than if you deal with all water. Or if you have H2S, you might have a different gasket again. So a picture of these heat exchangers is on the left. And these things can be as tall as this room is and however long they need to be, or they can be fairly short. They can be rated to 500 PSI to work with flowback, or they can be rated to 50 PSI for a very low pressure system. They tend to be, plate and frame tends to be more efficient, but it also tends to be more expensive as well, particularly if the metallurgy the chemistry of the fluids you're dealing with means that the metallurgy has to be very specific so that scaling isn't the problem. The same issues with scaling, and I've got some examples of this here later. The same issues that oil and gas has with scaling are the same issues geothermal has with scaling. This is an example of what a shell and tube heat exchanger looks like. These things can be very small. They can sit on the back of a flatbed truck like this one. But these are generally higher flow, can work at lower pressure. They're a little less efficient usually, but also are cheaper and way easier to clean. So depending on what the application is, shell and tube might dent your thermal efficiency a little bit, but your LOE will be lower. So like anything, like any sort of production engineering analysis, the economics sit against the efficiency and work out. So this is an example of what can happen in geothermal when it comes to scale. So this is the equivalent of lots of fast food for your tubulars. And if that is silica scale, like on the right, and that's a 45 centimeter interior diameter pipe, by the way, that is a peanut butter like putty. And so that can be physically cleaned out, not too difficult. You wouldn't want to let it get to that. But that becomes some of the world's most expensive scale. That's your mud mask. That is the mud that keeps your skin hydrated if you go to the spas and ice. The barium scale on the left, forget about it. You're drilling a new well if it gets to be that bad, I think, or doing a very expensive physical scraping of that, because that sort of scale getting to that point would be very difficult to remediate with anything but physical scraping. And of course, there's artificial lift. So because this is subsurface energy involved in fluids, we have to get those fluids to surface. There are companies working on downhole heat exchangers, but until those become commercial scale, we'll be continuing to work with getting either working fluids to surface in a closed loop sense or getting water to surface. So natural flow is obviously best for economics, just like oil and gas. If it just arrives on surface, great. You don't have to worry about getting it there. The challenge with geothermal is you tend to need a lot of volume, especially to make electrical power. So electric submersible pumps tend to deliver the best flow rate, whether they're induction motors, which are usually tuned to a specific hertz frequency and hence a specific volume to lift, or permanent magnet motors, which are more efficient over a wider range of flows. But you tend to pay for it in energy. So if you can gross 10 megawatts, you might be spending 5 of that just to get your fluid to surface. So artificial lift is one of those areas you can't avoid when it comes to looking at a full scope geothermal opportunity. There are line shaft submersible pumps where the line is a shaft that goes down into the subsurface, sometimes up to 1 or 2 or maybe even 3,000 feet, but the longer the dicier. They deliver better efficiency than ESPs and are more power efficient, but tend to be a little limited on the depths they can work with. So overall, with the concept of artificial lift, beware of parasitic loads. An example of that is that there's a Canadian government-funded geothermal plant going in the Williston Basin, just over the line in Turkey, Saskatchewan. And they were aiming for 50 megawatts, but they realized they'd be spending 30 megawatts on lift. And then they found they had entrained gas in the water system. So they're burning that to make more power. So it's a full energy operation going on there. And then lastly, we can talk about direct use a little bit. And direct use is sort of power generation because it doesn't involve super fancy technology, but it's all sorts of applications that if you buy power off the grid can consume a lot of power. So direct use can be very efficient for industrial processes, as well as even down to residential heating. So this is everything from drying drywall, to food processing, heating and cooling buildings, and doing spas. Of course, in Colorado, we know about pretty much any town ending in Springs has a spa like this one from Glenwood Springs. But there are all sorts of direct uses, and the higher you go in this chart here, you're into power generation, but greenhouse, aquaculture, bathing, agriculture, modular agriculture, there's all sorts of things. In Iceland, a few years back, this on the left, this is a pie chart showing their spectrum of direct use. Of course, snow melting is right up there, swimming pools. But in Iceland at the time, notice electricity generation, which is in yellow, was only 18% of the total, and space heating was nearly 60%. So there could be a lot of savings, whether you're measuring your savings in dollars based on an electricity bill or in carbon reduction or whatever metric you're choosing. Ignoring direct use when it comes to space heating is you're leaving a lot of money on the table potentially. So mineral waters are another aspect of it. I'd mentioned the most expensive scale deposit in the world, which is the mud mask from the Blue Lagoon in Iceland. It's 4,900 kroner for not very much mud. I don't have the exact size. That's a picture of the Blue Lagoon on the right. That was the site of last year's World Geothermal Congress, about half an hour from there. So there was an official field trip to go drink at the bar and bob around in that. And the Blue Lagoon turned out to be kind of an accident of industry, in the sense that what you don't see to the left of the image is a very large 50, 60 megawatt geothermal plant. And some of the employees back in the late 80s had been surreptitiously dipping in the outflow lagoons. And they realized their skin was great after they were doing this. And it was curing psoriasis, and their skin was just perfect. And they said, wait a sec, we can market this. This isn't just an outflow pond. Without too much change, but adding a swim up bar, as you can see, they've made it so geothermal heat pumps, and the larger issue of HVAC is something I talked about earlier. It can, according to the DOE, it can add up to 40% or be 40% of the building's total energy use. And so there are companies that will do this for commercial buildings, will do it for homes. And in a nutshell, the ways this can be done is vertical closed loop systems, like on the left. The middle one, horizontal closed loop systems, whether it's again for commercial or for a house, or closed loop systems that you just throw into a pond. So you have the more heating and cooling you need, the longer the line is, whether it's sitting in a pond or whether it's buried in the subsurface. But then that allows for the heat exchange. Now you can't go into your house and like crank up the heat and get instant response. This will take like a day or so to respond. But it's one of those things where once you keep your heat really constant in the building, it will be extremely efficient. And then to wrap up the talk here, we can talk briefly about the idea of geothermal on other planets, because that is a serious point of research in the planetary community. We don't need to talk about Venus. There's really no need for the thermal side, with the atmosphere at ground level being about 850, something like 9 or 10 times, if not more, the pressure of Earth's atmosphere. On Mars, that is the closest planet to Earth in the sense of, or most similar, but it's 2% the density of atmosphere. So you could probably do an air-cooled geothermal system there, because you've got, as this shows from the latest weather from Gale Crater, which is a real NASA website. For example, last week, high of 23, low of minus 92. So when air cooling, you'll get some variation day to night across that time. But the lack of density might mean your fan systems have to be a lot larger. I'm not going to say 98% larger, but considerably larger. One big question on Mars is there an active convective system in the deep subsurface? And there was hope that the Mars Insight probe was going to measure that. And their small coiled tube drill rig that was going to go something like 2 meters went, I think, 3 centimeters. They deep flux from the subsurface, but that'll have to be for the next mission. But with a low of -92 overnight, liquid CO2 could be, you could use the working fluid, so you wouldn't have to use water necessarily. And then there's one of the Soviet pictures of the surface of Venus that was taken before the lander melted, which occurred, I think, 2 hours in. So in summary, we talked about the differences between petroleum and geothermal systems, kind of noting the real focus on, obviously, thermal source and quality, and then reservoir issues. So migration and preservation of those hot fluids and those ability to flow to replace them, as well as the general flowability of reservoir. We talked about how sedimentary systems have lots of data, but the correction of bottom hole temperatures is really important, as it is in oil and gas as well. And when it comes to technology, steam handles the really high temperatures, and organic systems, organic Rankine cycle, handles those systems between about 150 Fahrenheit and 300 Fahrenheit. And then you've got issues around scale. You've got issues of what heat exchanger to use and other sort of technology applications. So for more information, the big US geothermal professional society is called Geothermal Rising. Strangely, they're based out of New Jersey, but they do all their work in Reno, Nevada. But they're the sort of APG or GSA, if you will, within geothermal. The major international professional society is the International Geothermal Association. They're sort of variously based in Belgium and Germany. And they put on the World Geothermal Congress, which used to be every 5 years, and now is every 3 to 2. So a year ago, it was in Reykjavik. In March of 2023, it's in Beijing. And I think then there's 25, 27, and so on. So the major conference is the Geothermal Rising Conference, which was the exact same weekend as Image this past, at the end of August this past year. So there was a lot of push within Geothermal Rising to watch when Image was and have it not be that weekend. Because there's so many oil and gas people who were at GRC. And then, as I mentioned, the World Geothermal Congress in March in Beijing. So with that, I can take questions from the online audience as well as from here in person. I have to end, of course, with ScienceCat and with a thermal joke from ScienceCat. So I've recently decided to freeze myself to -273°C. My family thinks I'll die, but I think I'll be okay. So with that, thanks for your attention, and I'd love to take your questions. Chris.
And with the water, you're managing brine, fresh water.
The question is, what sort of water do we manage in geothermal? Is it brine or is it fresh water? And it really varies by basin, I would say. It's in the Williston, it's going to be really, really briny. In the Delaware, it's going to be briny as well. If we're dealing with geothermal on flowback, where the unit would move every 4 to 9 months, let's say, then that would be your standard flowback. You'd have emulsions, you'd have oil and gas in that, but you'd also have essentially fresh water going into brine as you head more towards surface water. Or sorry, subsurface water. Yes, Holly.
Do you have to get 2 sets of permits, one for pulling the warm fluid out of the ground and another one for injecting it? So it's like you have to go through 2 complete different workflows. But you can't have all of that to do.
So the question is, what do permits look like for geothermal, and do you need multiple permits for the geothermal side versus for oil and gas side? And the answer is yes. So you don't need a permit necessarily for the water, because the water is not going off site. It's not being beneficially used, as the phrase is. But if the power or thermal power or electrical power being produced is going off site, say on the grid, then someone needs to get paid for that through a royalty. And that happens at the BLM, at the federal level with the BLM, and that would happen at the state and private fee level as well. But if it's just being used on site, let's say, and not going out at all, someone's not getting paid for it, then that, the asterisk is check with your land professional and your regulatory professional. But in a lot of states, you tend to not need a geothermal permit for exclusively on-site use.
So,
John.
which leads to two questions, actually, but the first one related to that is the new geothermal project would potentially have to go through the UIC permits, which would be injected law.
Yeah, so the question is, would a new geothermal project have to go through a new UIC or injection permit process? And the answer is maybe, if the existing UICs or UIC can handle it or can be moved up, then I think you'd sundry that. If you're going from 6 to 60,000, like the project is at Blackbird, Nevada, then that will involve an additional, well, at least, if not two, and then involve more UICs as well.
The second one is probably more of a sort of a small scale thing, but think about, is there potential resource with steam plants, oil and gas, instead of potential geothermal resource, but it is a pretty small scale.
So the question is there an application in steam floods and in EOR kind of more generally? And the answer is yes. I think with the one caveat or challenge with the steam flood is that you want to lower the temperature of whatever's coming out of the ground to the optimal process flow temperature of the facilities on site. You wouldn't want to lower it too low and then have to put more heat into the system to drive the steam flood. And we've looked at projects where we've been asked to, the projects are currently paying pole power to cool the fluid down to the optimal process flow temp. And ORC equipment, flash steam as well, can lower that and make power so that there's no added energy input needed.
Just as a matter of curiosity, can you tell us what transitional energy is up to?
So the question is, as a matter of curiosity, what is transitional energy up to? And so transitional is up to geothermal as a service, generally for oil and gas clients, in two realms. One, clients who want either power generation or carbon reduction as their primary goal. And the other is for clients who right now buy or rent fluid chillers so that they can make pipeline spec. The fluid might come out of the ground at whatever temperature it is, but the poly will melt at 150 or melt at 120. And so we'll use this ORC equipment to lower that temperature, make power as sort of a secondary goal, and come in at a price point very similar to the chillers. But longer term, the company's vision, my vision for the company is to get into being an independent power producer as the utility term is for it. So owning fields and making power at megawatt scale. And functionally, we'll probably end up doing both with two different business lines. The company is about 3 years old and the employees are getting paid, there are benefits. It's starting to feel like a real job. So it's been fun to go from a labor, night and weekend labor of love with a great team to something that feels like work, for better and for worse.
So, about 15 years ago, DOE had a field conference in Casper at the Teapot Dome, where they were partnering with oil and gas companies called Geothermal in the oil field, and they had a semi-trailer mounted heat exchanger where you can take your produced water and send it through the dual binary cycle and then produce electricity for remote location. But it was about the size of a semi-trailer flatbed. As technology improved, where it's smaller.
So the question is, comment question, that the DOE had a facility near Teapot Dome north of Casper at the National Oilfield, Rocky Mountain Oilfield Technology Center, where there was a long-term test of ORC equipment, of binary cycle equipment. And those things were semi-trailer size at the time. The question was, has that technology changed or become smaller in size? And the answer is yes. A lot of it has to do with the particular heat exchange technology used. So the semi-trailer aspect of that was a big shell and tube heat exchanger. And the smaller ones are the blatant frames. And then another aspect of it, of these ORCs, because it's a condensing unit, you can use an air radiator to condense down, which is big and has all the fans on the back. Or you can use any form of shallow surface water or groundwater. And so if you can use water cooling, then that makes the footprint quite. For example, a unit that is makes 300 kilowatts now, the unit itself is about 8 feet, a cube that's 8 feet on the side. But the cooling fans might be 30 more feet if you're doing air cooling. But the energy density has gone up. The price has come down in the intervening 15 years, mainly through what's known as the waste heat market. So steel mills, engine ship rooms, even, believe it or not, morgues and mortuaries. Any place that has excess heat, if you know what I mean, captures that heat and tries to do mechanical work with it. And so because that industry is fairly mature, there's been a lot of innovation on the refrigerant side, on the hardware side as well, which has shrunken that footprint.
At that time, there was a oil and gas company that was looking at the Raton Basin to have a closed system where one well was injected, the other, and they capture the heat, reject. But for an oil and gas company, the rate of return on their investment was years rather than months.
Correct.
And especially when you're selling electrical back to the grid at wholesale prices, pennies per kilowatt. Is it feasible now, or?
So the comment is the Raton Basin was hot, so to speak, 10 plus years ago with interest from an oil and gas company. The Raton Basin is, folks are still looking at the Raton Basin specifically. The value of baseload renewable energy tends to get a premium. So if coal-fired power is 2 or 3 cents a kilowatt hour, baseload could be 5, 10, 15 cents per kilowatt hour, sometimes more. California is looking for a gigawatt baseload renewable power. They didn't say they want geothermal, but geothermal is the only renewable baseload. And I've seen contracts in California in the public sphere up to 40 cents a kilowatt hour. So it starts to get economic at megawatt scale when you're selling at 40 cents kilowatt hour. And I think that's made possible by the interest in ESG, environmental, social, and governance. It's made possible by folks who are willing to pay that higher price to say we've sourced baseload renewable. Whereas 5, 10 years ago, that was not, there wasn't as much of a differentiation in the market. Yes.
Building on that point, talking about the value of baseload power, right? 7, but I read a paper earlier this year that built on the work from Vincent Hill in the 90s, talking about how when they shut in these reservoirs for a while, and then they open them up again, they can produce really well. There's no detriment to the performance. The implication is that geothermal works just as well as a dispatchable resource. The more renewables you have on the grid, the more you might want something that can scale up and down as needed. So I'm curious if that could push the economics, or what your thoughts are that economics can take a tipping point in the next decade and start to scale up, especially taking dispatchability.
So the question is around the dispatchability of geothermal power, noting that wells can be shut in for a while, and there's no ill effect on flow and certainly on heat. And so doesn't necessarily just have to be a baseload; it could be dispatchable. Yeah, the answer is yes, absolutely. It would depend, and it's all about whereas selling a barrel of oil is selling it, and you can hedge that. Setting up power contracts or power purchase agreements, PPAs, is their creativity around that is kind of the next step. So you can have tiers of baseload. You can have a well shut in entirely until needed for dispatch for the hottest days in July, let's say, and you can get pricing accordingly. So absolutely works, kind of works in both directions there. Sarah.
Think about the warm back concept. And think of when you drill, you have mudcave and infiltration. So you start getting heat transfer and warming that up from the reservoir. There was like a cone of cooling
it can be a thing. So the question is there thinking about warm back, is there a cone of cooling, so to speak, that occurs around a wellbore as it's drilled and as mud is circulated in the wellbore, particularly if the well's not balanced, I think, or if mud cake or filtrate doesn't occur on the wellbore wall. That's probably the mechanism or the process behind some of that warm back, and why it tends to vary. Why I think it tends to vary with kind of the pour-perm relationship. So, Gulf of Mexico, Darcy scale stuff versus something tighter, you'll have a different relationship on that warm back. So that gets into the idea of heat mining, which I'll talk about very briefly. The idea that if you put an injector and a producer pair next to each other and inject your cool air water, after you've made power down one and you're pulling it right out the other one, obviously at some point fairly quickly, your hot water is not going to be hot anymore. You're going to be cycling the molecules themselves. And the further and further away you put those two wells in a doublet, the more time it takes those molecules of cool water to make it through, but also the more tortuous the path is, the more effective that can be warmed up either by convection or conduction. And NREL did a great study in 2017 in the Lions here that showed when you're at least a half mile away, you don't get appreciable heat mining until about year 60. And I'll defer all the detail to that NREL paper, but that gets the idea of thermal, those of you who do geologic modeling, particularly dynamic modeling, you'll have a bright future in geothermal, because understanding the thermodynamics as well as the flow is really important in making sure that you have a sustainable resource there. Let's see, Matt, did you have a question? Randy?
I heard that there were some new drilling technologies that laser drilling that can drill really fast and really deep. How might that technology come in of accessing deep sources for some of your?
The question is around, are there new drilling technologies out there that can drill really fast and really quick, particularly laser technology, that could really revolutionize access to deeper wells? And the answer is there's a company called Quaise that is pushing laser drilling. I would wonder about the return on energy investment, so to speak, in those in order to do that. But I'm excited to see what happens there. There's also in kind of more conventional type, there's a lot of work done on drill bits. Because particularly for geothermal drilling that's done in igneous or partially igneous terrains, that can really chew up a drill bit when we're used to sedimentary systems. So achieving higher ROP in what in oil and gas we would consider really challenging terrain, I think is also kind of, that's probably a little bit closer to the fore in terms of being commercial. So, yeah. Rob?
So can you speak to the macro picture for geothermal in the US? I mean, are there a lot of companies in your space trying to do similar things? And does the EIA have any projection for growth for geothermal?
The question is, from a macro standpoint, what does growth industry look like? Are there companies doing what Transitional is doing? The answer is there are folks getting into that space. But there are folks all over the space focused on the technology of drilling, for instance, to answer the previous question. There are traditional geothermal companies looking to do what they do with cheaper or less CapEx and cheaper LOE. But I think there's some technology, there are companies looking at downhole heat exchangers or refrigerants. So just like there's a lot of technological innovation in oil and gas, that's starting to happen in the geothermal space as well for the physicality of it, the widgets, as well as for the less so, but increasingly so on the application side. And I think not all of the companies will make it, just as technology companies in oil and gas space don't always make it. But I'm really excited to see the idea that the innovation generally across both industries will be a tide that lifts all boats, and that the geothermal space as well as the oil and gas space will benefit from that innovation. So I'm excited. The next 20 years, next 10 years should be really exciting. Let's see. Yes, Donna.
Could you speak to the Forge project and kind of the preliminary results coming out of that?
The question is, can I speak to the Forge project and the preliminary results? I can't speak too much to the details. there's a great websites, and there's always a kind of a constant stream of papers that come out. But a lot of the areas of innovation there have been in the drilling, in completions, as well as a little bit on the power generation side. So it's been subsurface focused, subsurface engineering focused. And I think early time, the 90s and early 2000s, there was a focus on how to delineate effectively with seismic techniques, with magneto and tellurics, et cetera. So not just from a sedimentary perspective, but also from how would you take that into the mountains of California, for instance. But I think their websites and papers would do a lot more justice than my summaries. Yes, sir.
Yeah, just curious, are there conversations or debates on how to pay people for the heat that you harvest from under their minerals or their surface?
So the question is there a conversation around how people get paid for the heat from their is it treated as a mineral, is it treated as a surface? Different states treat it as differently. In some cases, it's alongside the water law. In some cases, in Colorado, my understanding, it's a surface use. In Nevada, it's the heat itself is a mineral, but separate from the water. So it's an area where the regulatory uncertainty as to how it's treated is probably one of the bigger hurdles to getting something done. With an oil and gas permit, at least on federal lands, you have the oil and gas operator has the right of first refusal for a non-competitive geothermal permit, a geothermal lease rather, and then the state handles the permitting. A lot of times, because it's a box that goes on site, the permitting side of it is a sundry, since there's no kind of you're not taking up, you're using a brownfield site, an existing pad, let's say. But from a regulatory standpoint, again, if it's not going, the geothermal is already being produced. So if the benefit of that doesn't leave the pad, it tends to be handled by the regulators as it's already there and no one's getting paid for it. Even if the operator is pulling less off the grid as a result of it. It's only when money starts changing hands is when the regulators or the Office of Natural Resource Revenue gets involved.
Yeah, I would think the owners of South Texas are gonna want to get paid for it.
It tends to be, royalties tend to be on a percentage basis. So oil and gas has geothermal has higher energy density than say wind or solar, but lower energy density than oil and gas. But on a percentage basis, if there's 10 cents a kilowatt hour going out total per kilowatt, then maybe it's 2% of that is a really small number. But if you make 10 million kilowatt hours in a month, 2% of that small number does add up. Okay. Any more questions? See, are there questions from the online audience? Look at the chat, and I'm not. Let's see.
I just have a comment on Warmback. In oil and gas, sometimes logs are running cased holes a long time after wells were drilled. And those are if it's been a while, a couple of months, it's closely reflective of the rock areas. So that's, and often the cased hole logs haven't recorded the development. So that's a goal.
The comment is that cased hole logs, whether they're CBL logs or any other form of cased hole logs, because they're done months after the well is drilled, those tend to have close to a true reflection of the reservoir temperature. And I would wholeheartedly agree that when you can find CBLs that have temperatures on them, those things are gold. Absolutely. Well, thank you all for your attention, both here and online. And both my email and the company's info account is here on the slide. So feel free to get in touch if you have any questions. And thanks again.